Welcome to the lecture on characterization of flow in actual systems. So, we talked about the idealized systems and we talked about the plug flow, ideal plug flow, and also the ideal mixed flow, purely mixed flow. But then actually in actual system the flow is in between these two extremes, and we must have the models which needs to be followed. So, the longitudinal mixing is non-existence, as we discussed in the plug flow system ideal system. We have seen that it is that system in which there is no longitudinal mixing, and in the case of well mixed system it is mixing is the maximum, and these two are basically the two extremes and the actual flow systems that lie between these two limits. So, you will have the models with parameters and you will have to have the adjustments so that when you do the experimental analysis, then the prediction of that model should match with the experimental data. So how to develop those models and how to do the adjustments that needs to be seen. Now, for that there are different models, and certainly we will be talking about the values of the best fitting parameter, which will be most accurately describing the mixing in the vessel. So that is regarding the output characteristics. So, in that we are going to have the study of the longitudinal dispersion model. So, in actual there will be dispersion even in the longitudinal direction, whereas in plug flow we have assumed that there is no longitudinal dispersion. So, the tracer which is coming at the inlet, so you will have after some time it will be appearing at the outlet, there is no longitudinal mixing. Whereas when we talk about the dispersion models, so in the longitudinal dispersion model, in that the tracer will flow through the system with certain longitudinal mixing. So, in plug flow there is no longitudinal mixing and travel some distance in time t1 and t2. So, as you see that it will be t equal to 0. So, it is here, and at t1 and at t2 also it is maintaining its identity. So, that is basically the plug flow, ideal plug flow. However, when we talk about the actual case, so in that you will have the dispersion when there is dispersion in the longitudinal direction. So, it is also known as dispersed plug flow. So, it will be assuming that there will be certainly some extent of turbulent eddy dispersion which will be occurring in the plug flow in this case. So, what you see that you see at t equal to 0, this is how the tracer was, and at t equal to t1 you see that there is certainly some dispersion in the longitudinal direction, and at t equal to t2 when it has gone. So, you will have again the dispersion. So, it will the tracer will be looking like this. So, it is because of the longitudinal dispersion that is occurring in the actual case. So, similarly, if you go for even the step input, so that was the case in the case of pulse input, but if you go for the step input also. So, in the case of step input, if you see, if your flow is like going here, so this will be flow in, and this you will have the flow out. So, in that case also, if you are so you will have t equal to 0 here, and I mean ideally you will have after. So, when you have the normal ideal plug flow, in that case when you go for step inputs after some time, that is your residence time. So, you will have automatically the concentration will rise. So, your dimensionless concentration will come to 1, whereas if you go for the dispersed plug flow. So, in the dispersed plug flow, if you come to T equal to T1, so at T equal to T1 there will be certain dispersion. So, this will be T equal to T1. Similarly, you will have T equal to T2, you will have this way the case. So, accordingly it will move even in the case of step input. So, what happens that when we talk about these models, so here you have the longitudinal mixing, and that can be represented, that will be the model will characterize this longitudinal mixing. That it will be characterized by one dimensional equation similar to the fixed law of diffusion. So, there will be diffusion that is going on in the longitudinal direction. So, it will be similar to that one dimensional fixed law of diffusion. So, here there will be again you will have the constant of proportionality, and this constant of proportionality will be known as the eddy diffusivity. So, you will have so this model which will be using. So, that will be model characterizing the longitudinal dispersion or longitudinal mixing, and this is by the 1D one dimensional fixed law of diffusion, one dimensional equation that is similar to the fixed law of diffusion. So, as you know, you will have in the fixed law of diffusion also you have the diffusion constant. So, here also you will have a proportionality constant, and the proportionality constant will be known as the eddy diffusivity. Or we also call it as the dispersion coefficient, that is dE. So, in this case whatever constant of proportionality we use, that is known as the dispersion coefficient, and this dispersion of this tracer which is there in the continuous flow system. So, that will be resulting because of this eddy diffusivity, eddy diffusion as well as the bulk flow. So, if you talk about the unsteady state concentration, so that equation, can be written as the dou C by dou T. So, that will be change of the concentration, that will be dE times dou square C by dou x square and minus U times dou dC by dx. So, that is the unsteady state equation for the concentration that can be written. So, that dE is basically the dispersion coefficient. So, here U is the basically bulk flow velocity. So, this is bulk flow velocity of the fluid, and x is certainly the distance in that x coordinate. So, x will be distance, and it will be varying from 0 to the length. So, that is L. So, it will be 0 to L. L is the vessel length. So, this way you will have these terms. So, if you try to further write this equation in the dimensionless form, so T should be written in terms of theta, and similarly you can have x will be replaced by the term y. So, y can be taken as something x divided by the characteristic length or length of the vessel. So, L. So, if you find, so if you rewrite this equation, so you can rewrite in dimensionless form. So, in that case you can new dimensionless terms you can say term. So, you can write dou c by dou theta, where the theta will be dimensionless time. So, then you will have dE upon UL and dou square c by dou y square minus dou c by dou y. So, here you are what you have done is you have non-dimensionalized. So, you have non-dimensionalized by so y will be the dimensionless distance, and that will be equal to x by L. So, you have divided x by the vessel length. So, that is y, and theta is certainly t upon t bar. So, that will be t into u by L. So, this way you can have the equation that is the in the non-dimensional form. Now, if you see this equation, in this equation you have the term that is dE upon UL. So, this dE upon UL, it is a term that is dimensionless group, and this term is known as the dispersion number or vessel dispersion number. So, we also call it sometimes as the dispersion number or the vessel dispersion number. So, if you look at this term, this is nothing but this is the inverse of the Peclet number term. So, in Peclet number you have the convection ratio of convection term to diffusion term, whereas in this case you have diffusion term to convection term. So, this is basically the inverse of the Peclet number term, and this is so it will be talking about the extent of longitudinal dispersions. It will be talking about the longitudinal dispersion in the sense that if its value is more, so longitudinal dispersion is more. So, accordingly your values will be coming. So, it is not the molecular property of the system basically, but it will be depending upon the flow condition of the system. So, depending upon the flow condition, this d by UL, that will be changing. Now, if you talk about this value of this dispersion number, so depending upon the different value of the dispersion number, you will have the different shape of the F or the C curve. So, that can be seen, and more its more pronounced effect can be seen in the case of C curve instead of F curve. So, when your d by UL, that will be approaching to 0. So, it will be limiting case that will be towards the plug flow, whereas if it is approaching towards infinity, then it will be representing the well mixed flow. So, that is how the significance of these two these two extreme values of d by UL carries. So, if you when your dE by UL, when this is approaching towards 0, it means the dispersion is negligible. So, dE term is that is negligible. So, in this case so once it is negligible, so you will have the prevalence of the plug flow. So, plug flow prevails. On the other hand, if your dE by UL is very large, so if the dE by UL is approaching towards infinity, it means dispersion is very high, and the maximum possible. So, maximum dispersion, and that will lead to the well mixed flow conditions. So, that is how your that is the significance of this number d upon UL, that is your dispersion number, and you can we will see that how by changing this dispersion number your there will be change in the shape of the F curve or the C curve. So, if you talk about the F curve, so if you take the step input or F curve, so so the equation which we have seen earlier, this was the equation. So, this was the concentration equation. Now, this equation can be solved, and you will have to have the initial as well as the boundary condition. So, this equation if you solve using the initial as well as the boundary condition. So, solving equation using initial condition and boundary condition. So, if you have the initial condition, so you will have initial conditions are like at t equal to 0, you will have C equal to 0 at x is more than 0, and you will have C equal to Ci at x equal to 0. So, initially you will have that condition, because you are putting the tracer there. So, and then if you have the boundary conditions also, and the boundary condition will be like you will have C equal to Ci at x equal to 0, and then if you go to x equal to L, so that will be C at x equal to L. So, if you solve in this with this initial and boundary condition, that particular equation, then you are getting the solution of that equation as F equal to C upon Ci. So, that is your F value, and this value will be half of 1 minus error function, and you will have 1 minus theta upon 2 into dE upon UL, and this to the power 1 by 2. So, this is how if you take this as so this becomes the value of F when you solve that concentration equation, that was dou C by dou T will be that was d times dou squared C by dou x square minus u times dC by dx. So, this now if you see, so this is nothing but the equation which will be relating to the dimensionless time with the dimensionless concentration F, and if you plot for the different for the different dE by UL, that is dispersion numbers. So, what you see is that if your there is no dispersion, we had seen that when you have no dispersion, in that case it leads to the ideal plug flow. So, what will happen, this is theta and this is value of 1. So, your it will be coming like this. So, so it will come here, and then at this point itself it will go. So, this value is 1, this is F, and this is theta. So, this is theta, this is 1, this is 0.5, this is this is 1.5, and this is 2, like that. So, this flow will be showing. So, here if it goes like this, this is dE by UL is 0. Now, as the dE by UL will be increasing, now the other extreme value will be dE by UL as completely for completely well mixed flow. So, that is for dE by UL in infinity, and that will be, that model will be going like this. So, this is the equation for dE by UL equal to infinity. Now, you will have the equations. So, you will have one extreme as the plug flow, another is the well mixed flow. So, otherwise you get the the curves like this, or you get the curves like this. So, as the so from 0 it will be increasing, so it will be 0.00. So, for this it will be d by ul, it will be 0.002. Here d by ul will be 0.02. So, this is by the researchers. They have found experimentally that for the different values of the d by ul, as it is 0 it will be the plug flow, and as it is going towards infinity you will have the value that is for the well mixed flow. It shows like this, because this dispersion has started here itself, whereas for 0 it has not happened, and at the mean residence time of theta equal to 1, that is theoretical mean residence time, all has come out with concentration of 1. So, that is what the meaning of the dispersion number or the vessel dispersion number, its significance is. Now, if we try to see for the pulse input. So, if you go for the pulse input, or you analyze the C curve. So, we have to further solve that equation, that is dou C by dou T will be d times dou square C by dou x square minus, again you will have dc by dx. So, that was this equation. So, if you solve this equation, so you will have, again for the pulse input you will have the different boundary conditions, and you will have to solve. So, when we talk about the pulse input, so we are talking about the different cases, and if we take suppose the closed vessel. So, you may have the case of closed vessel or the open vessel. Now, in the closed vessel you will have the input from at the input as well as at the output there is no dispersion. So, the tracer will come, it will go out, whereas there will be dispersion going on in the vessel, whereas in the open vessel means you will have the the stream which is open. So, dispersion taking place here also at the inlet as well as at the outlet also. So, if you look at the in a closed vessel. So, in the closed vessel you will have again you are so in continuous casting operation, the tundish can be taken as the closed vessel, because your tracer inlet is from one side, that is from ladle it is entering into the tundish, and then the die is coming out through the tundish outlet. So, the closed vessel by definition we must know that in the case of closed vessel which has a finite length of L, and in which there is no tracer movement, no tracer material moves into or out of the vessel boundaries by dispersion. So, that is the definition of the closed vessel. Now, in this case the eddy diffusivity which will be there at the inlet and outlet, that will be 0. So, your eddy diffusivity at inlet and outlet is 0. So, what we do is, again you solve that concentration equation with the boundary condition in the closed vessel, and in that case you get you get the mean as well as the variance of the curve. So, what you see is you get the family of curve. So, you get mean theta bar as 1, and the variance sigma square of this family of curve which you get. So, if you solve it numerically, so you get the sigma square as 2 into dE by UL, and then minus 2 into dE by UL square times 1 minus exponential minus of UL by dE. So, that is the numerical solution that has been reported for when you solve for in the closed vessel. So, closed vessel will be characterized by this kind of system. So, you will have the vessel here, and so you will have inlet here, and then you will have outlet here. So, from here you will have inlet, and from here you will have outlet. So, you will have tracer output signal from here. So, at this point you will have tracer output signal, and this is your input signal. So, this is your tracer input signal, and this is your tracer output signal. So, that is how you see that in this case what you see that your mean residence time, that is theta bar, that has to come to the unity. Now, if you take for the open vessel, so in the case of open vessel, so it has no discontinuity at the location of the tracer injection or the tracer concentration measurement. Now, in this case you will have the selected experimental length, so that will be your open vessel. So, in that in basically in the infinite vessel. So, what you do, so in the case of open vessel where the C curve has been found, this is found to be C equal to 1 by 2 root pi theta into dE by UL. So, this is by the researchers that and that is reported by Sai and ME. So, this is the value which is coming. So, this will be minus of 1 minus theta square divided by 4 theta into dE by UL. So, this is the solution of that equation 4.13, and in this case if you try to find the mean and variance of the family of the curve. So, the mean and variance will be coming as 1 plus 2 times dE upon UL, and the variance is coming as 2 into dE by UL plus 8 into dE by UL whole square. So, this is how the family of curves can be drawn for the pulse input. And if you look at the dispersion model with a small amount of dispersion, which is that consideration being taken away. So, if you consider the case, I mean we are going to have the case for the dispersion model where for the dispersion number value is small. So, dispersion model for small extent of dispersion. So, where there is a small dispersion. So, in that case what happens, and for a closed vessel. So, the closed vessel which is normally for the case of tundish flow. So, in that case the C curve is normally having a Gaussian type of profile. So, Gaussian type of RTD will be there when you have low dispersion, small dispersion in the so your C profile will be like the Gaussian dispersion, I mean Gaussian type of profile. And in that case if you do the solution of that concentration equation. So, that equation if you solve it, that has been found to be as C equal to 1 by 2 root pi into dE by UL, then exponential of minus of 1 minus theta square divided by 4 into dE by UL. So, that is what has been reported, I mean found out that this is how your concentration family curve looks like, and for that your mean and variance. So, if you find the mean and variance, that mean becomes 1 and variance becomes 2 times dE by UL. So, if you try to draw the these family of curves, and for the different value of d by ul. So, for the large and small value of the dispersion in a closed system. So, once you draw, then your C curves look somewhat like this, as you know. So, as you know that when you have if you might have you can recall that when in the case of well mixed flow, so completely ideal mixed flow, your curve starts from here. So, if you have this is as 1 and this is 2 and so. So, in the case of well mixed flow, it will go like this. So, this is for the maximum d by ul. So, your so for this case d by ul will be infinity. So, that is representing the well mixed flow. Now, if you have the plug flow, so now in this case this is theta. So, this is 0.5, this is 1, this is 1.5 and this is 2. So, in the case of the plug flow, as you know, so it will move like this. So, this will be d by ul, that is 0. So, there is no dispersion. So, that is your d by ul is 0. However, you will have the curves coming like this. So, and you have also curves going like this. So, if you see here, this curve is corresponding to where this curve will be d by ul, that will be equal to 0.2. And if you look at the another curve, so you will have you may go like this. So, this will be d by ul will be 0.002 or so. So, like that you will have the variation in the family of these curves, and as you go towards the d by ul values smaller and smaller. So, you will have the confinement, and for the 0 value your value your curve comes at theta that value equal to 1. So, this different values represent the different kind of dispersion, different extent of dispersion, and the family of these C curves can be drawn. So, this is about the actual flow characterization which takes place. We will be talking about the other aspects like about the calculation of the mean resonance time, and then its mean and as well as the variances in our coming lectures. Thank you very much.